Hello, everyone. So today begins it's a very exciting today begins trig. Okay, so trig is separated into two units, essentially trig functions and trig equations. Other schools, if you happen to be watching this video from other schools, it might be called trig 1 and trig 2, but usually it's separated into two different equations. Those of you who are my students and working through the book that we have we are starting on the title that says radian measure. But what I want you to notice is 4 pages behind that is called prereq skills for trigonometry. Those are things that by the time you come to us in 30-1, we would expect that you're decently comfortable with. So I really want to encourage you, make sure you do those 4 pages. Make sure you have a good understanding of them. And then if there's a gap somewhere, or if you have any questions, make sure you come and ask me about that. Okay. But today what we want to start with, there's kind of 3 things we want to do in this lesson. We want to deal with this concept of radian measure. And then we want to deal with how that helps us with a concept called arc length. And then we want to review angles and standard position from 20-1. Okay, most of that part I'm hoping will be a review, but it'll give us a chance to make sure we're all on the same page and we're all doing okay with each other. Okay, so this is not in your book, just a quick little history for you. Up until this moment, when you're watching this video, when we talk about angles, your frame of reference is a system of measuring called degrees. So if I went like this, you would say, hey, that's a 90 degree. If I went like that, you'd say, hey, that's a 45 degree, which is great. The problem is degrees is not really it doesn't really have anything to do with math. It's an arbitrary system. And by arbitrary, we mean the Babylonians cut a circle into 360 parts and said, hey, let's call one of those parts a degree. Okay, so usually in math, everything we do in math has some sort of mathematical basis from another principle or another concept. Okay, and the degree was not, it was completely made up. And it works for a lot of things. But when we get into deeper level math, the whole system of degrees kind of falls apart because it's not based on anything. So in the late 1800s, mathematicians and physicists saw the need for another unit of angular measure to identify or to aid in simplifying trigonometric calculus calculations. So this is very similar to, hey, when we measure lengths, we could measure in inches or centimeters, okay? We don't, like the length of the desk that I'm sitting at doesn't change whether I say it's in inches or in centimeters. It's just 2 different measuring systems to look at the same length. So it is with angles and radians. They're 2 different measuring systems to look at the same angle, okay? Okay, so how do we get to understand radian measure? We will work with, I'm in your book now, by the way, we will work now with a much more useful measure called radian. So that's your first blank there. Okay, so here's the definition. The radian measure of an angle formed is the ratio that compares the length of an arc of a circle to the radius of the circle. So an arc length just refers to a piece of the outer edge of the circle. Okay, so in the diagram I've given you here, you can see that I've labeled this guy here as theta. So this is the angle that I'm looking at, and it would be the ratio of the arc length, which is A here, divided by the radius, which is my R there. Okay, so theta, we call that a center angle or a sector angle, central angle or sector angle, which is an angle in a circle formed by 2 radii. Radii is just plural for radius. The radius is denoted by R and the arc length is denoted by A. Okay. Okay, so what we end up doing, I had just kind of said this in the previous slide when I was drawing it out for you, but it's essentially the measure of the sector angle will be the length of the arc divided by the length of the radius. okay? The length of the arc divided by the length of the radius. In a simpler way, we say theta equals A over R. Now, a couple of things I want you to know. Thing number one, this is on your formula sheet, okay? So this isn't a formula you have to remember. Thing number two, though, this formula is the definition of radians, okay? So you can't use this and get out a degree measure. Likewise, you can't put a degree measure in here. It has to be dealing with radians only, okay? So you're often going to get questions where we ask for the arc length, but we give you a degree measure. Well, you'll have to convert that to radians first. Or we ask you for the measure of an angle in degrees. You have to use the arc length in order to get the measure of the angle in radians, and then you'll have to convert that to degrees, okay? Now, we don't know how to convert that to degrees yet, so that's the next thing we need to do. We always have these conversion factors, right? Like, you know that 1 inch is 2.54 centimeters. So if you had 10 inches, you have 2.54 times 10 centimeters. You have this conversion in your head that allows you to go from one system into the other. So what we want to do now is we want to build a conversion for radians to degrees. Okay, so since an angle can be measured in degrees or radians, we must be able to convert between the two measures. Consider a circle with radius r. Let me draw one for you. A circle with radius r. Okay, I want to figure out this angle from here to here. Now, you know that angle in degrees. That's why I want to figure it out in radians, right? You know that that's 360 degrees. Okay. Now, we said that the radian measure, theta, will be the arc length divided by the radius. Well, theta then will be the arc length divided by the radius. Now the radius I'm just calling r, so I'm just going to leave it as r. But here's what I want to talk about. What would be the arc length if I started here and went all the way around and back to there? The arc length would be the circumference. Do you agree? Okay, so circumference of a circle, that would be the arc length of the whole thing. Circumference of a circle is 2 pi r. So I end up with arc length divided by radius, 2 pi r divided by r, but then my r's will divide out and I'm left with 2 pi. So that tells me that 2 pi radians and 360 degrees is the same thing, okay? 2 pi radians and 360 degrees is the same thing. So one complete rotation in degrees is 360, the arc length is 2 pi r, so the radian measure is 2 pi radians, okay? Which means we now have a conversion factor. 360 degrees equals 2 pi radians. Or to make that simpler, because both of those are divisible by 2, we say 180 degrees equals pi radians. Okay, 180 degrees equals pi radians. So this is the conversion that you'll end up using most of the time. Super important. If you are talking in degrees, you must have the degree symbol there, because by default, if there's no units given, you're talking in radians. So if you just wrote the number 180 and you didn't put that little degree symbol there, I have to assume that you're talking about 180 radians, and 180 radians is way different than 180 degrees. Okay, so make sure it's just like units, right? Make sure you have that there. Now the RAD for radians, we don't actually have to have that based on the conversation I just said. If there's nothing there, it's assumed to be radians. So you don't need units when you're talking about radians, but you absolutely need the units when you're talking about degrees, okay? Whoops, I gotta get my ink off there. Okay, so many of you probably don't even know what this is, but it's a Trivial Pursuit game piece. And what I wanted you to see, okay, 2 pi is 6.28. So it's really hard to visualize in our head, well, how big is 1 radian then? So if 2 pi is 6.28, that means really close to 6 radians would fit into a circle. Okay, not quite because it's 6.28, but close to 6 would fit into a circle. So if I took a circle and divided it into 6 pieces, which is what this game piece does, that's why I wanted to show it to you. Each of those pieces, each of those segments is roughly, not exactly, but roughly how big a radian is. Okay, so it just kind of gives you an idea when you're thinking about 1 radian. Think about a circle, kind of divide it, or think about a pizza if that's better for you. Divide it into 6 slices, and one of those slices is roughly how big in the circle a radian is. Okay, it's important that we can visualize things. Okay, so convert the following to radians, leave your answer as exact value. So I have 270 degrees. If I want to convert that to radians, I need to convert, or I need to multiply by the conversion factor. Well, we already know the conversion factor is pi radians equals 180 degrees. So like my choice is very simple here, even if you don't know what you're doing. Either I multiply by pi over 180 degrees, or I multiply by 180 degrees over pi. So now when you're looking at these two conversion factors, you're thinking, okay, which one is going to get rid of the degree for me? Well, because the degree symbol is on top here, I need it on the bottom here. So it's actually going to be this guy that I multiply by. Okay, so we go 270 times 180 over pi. Sorry, I just listened to what I said there. That's not what I meant. We go 270 times pi over 180. I had already established that, and then I just wasn't paying attention. So 270 times pi over 180. So then what happens is, essentially, you just think of this as one big fraction. It's 270 pi over 180, and you want to reduce the 270 over 180. Okay, this is not a moment in your calculator where you are pressing the pi button. I do not want a decimal approximation here. I want exact values. Always, always, always exact values unless you are explicitly told otherwise, okay? So we're thinking about 270 over 180 as a fraction. That's 27 over 18. Both of those are divisible by 9. So it'd be 3 pi over 2, okay? 270 over 180 reduces to 3 over 2. Okay, you try 315. Okay, you should have gotten 7 pi over 4. 315 over 180 would reduce to 7 over 4, and then you keep your pi on the top. Okay, let's go the other way. So now I have pi over 4 radians. Okay, so now my conversion factor flips, right? Now I'm going to multiply by 180 degrees over pi. That way my pi's will divide out, and I'm looking at 180 over 4. Okay, so 180 over 4 becomes 45 degrees. Don't forget your degree symbol there. Okay, you try negative 7 pi over 3. You should get negative 420 degrees. Okay, now I threw this one in too because you have to be careful that you don't get lost in just memorizing an algorithm. 5.2, you still have to multiply that by 180 over pi. The problem is the pi's don't divide each other out, right? Because there isn't a pi in 5.2. So this is an instance where you will physically have to type the pi button. This question didn't say leave an exact value. So you're going to go 5.2 times 180, divide by pi, and then round it to the nearest degree for me. And we would give you rounding instructions. And you should get roughly 298 degrees. So just make sure you're able to get the 298 degrees there. Okay, so again, that's 5.2 times 180 divided by pi. Okay, all right, so now determine an arc length subtended by 30 degrees and a radius of 5 centimeters. Leave your answer in terms of pi. So we have a formula. We have theta equals A over R. We know that we don't know the arc length, that's what we're trying to find, but we know the radius is 5, and we know that the angle, theta, is 30 degrees. Now, I can't plug that into my formula as 30 degrees because that's a degree measure, and the formula is radians, so the formula needs a radian input. But you don't even have to convert it as a separate part of the question. If it's 30 degrees, I'm just immediately going to call it 30 pi over 180. And now I have created it as radians, okay? So see what I've done there is I've just gone 30 times the pi over 180, okay? So that'll be 30 pi over 180, which is pi over 6. So I actually did do, I converted it first, but you don't need to. I could have just called it 30 pi over 180 right away. Okay, so on your formula sheet, we have theta equals a over r. So then if I want a by itself, I just multiply both sides by r. And that's where I'm getting the arc length equals theta times r. And then I know that theta is pi over 6. And again, you could have just as easily in your work written this as 30 pi over 180 first and done all that conversion together. And then multiply by 5. So leaving it in terms of pi, that means I'm looking at 5 pi over 6. So 5 pi over 6 centimeters. Don't forget to answer with units. You would get docked marks as an incomplete answer if you didn't have the proper units there. Okay. Okay. Determine the measure of the angle. So this time I'm looking for an angle and it's to the nearest degree. I know the radius is 1.8 and it subtends an arc of 50.2. That word subtends just means it's the angle is within that arc. So if I showed you a picture, if I just added to this picture here, and I'm looking at that theta now, okay, this angle subtends this arc, okay? That's all subtend means. Okay, so theta equals a over r, so we're going 50.2 divided by 1.8. Okay, now, if I want to have a fractional answer here, I don't want decimals. You can't have decimals on top and bottom of a fraction. So I'm just going to take my calculator, go 50.2 divided by 1.8, and just convert that to a fraction. Okay. Then I just also wanted to show you that I want to show you that the units work out here. So notice that my meters will divide out, and now I'm in radians. Okay. So I end up with 251 over 9 radians. Again, that is 50.2 divided by 1.8. Okay. Great, but that's not how the question asked me to answer. The question asked me to answer in degrees. So now I need to convert that to degrees. So I'm going to take 251 over 9 and multiply it by 180 degrees over pi. And then you'll notice that my radian unit, you don't have to have all the units in here. I'm just trying to show you that it works. The only thing you have to have there is the degree symbol. My radians will also divide it out, and I'm left with 251 times 180 divided by 9 pi. Clean that up and you should get 1,598 degrees. Now, here's a question. Is that possible? Can I go 1,598 degrees? And the answer is yes, of course I can. Because it just means I'm spinning around and around in a circle. I've gone around a circle more than once, right? Because one loop of a circle would be 360 degrees. Okay, good. A child's lollipop is in the shape of a rainbow. The stick is in the center of the lollipop, with its end being the center of the circle created by the rainbow shape. Calculate the perimeter of the lollipop, given the measurements shown. Round your answer to the nearest 1/10 of a centimeter. Okay, so it's super important when you're looking at stuff like this that you read the question, okay? For instance, lots of kids, when they see a question like this and their headspace is in arc length, they say to themselves, oh, okay, I just need, whoops, I thought I had that on. I just need this length from there to there. That's a nice big old arc. That's awesome, okay? But that's not what you need. You need the perimeter. The perimeter is that, plus that, plus that, plus that, right? The perimeter is the distance all the way around. So in order to do that, sorry, I wanted to hide that for a sec because I didn't want my work there. When I was turning my ink on, I was actually pressing the mouse. So if I want all 4 of those pieces, there's actually 2 arc lengths that I need there. And then these 2 straight pieces here. Well, the straight pieces are easy. They're 3 centimeters because that's marked clearly for me there, right? So I know I've got this piece plus this piece plus 3 plus 3, okay? But now, in order to get those arc lengths, I need to think about the circle, okay? The circle, the center of the circle would be right here, which means I'm actually looking at a sector angle that looks like that, right? And then this would actually be big piece of this outer edge of the circle here, okay? So I only gave you pi over 4 from here to here. Well, we're assuming the stick is in the center. So that means the whole angle that I need would be pi over 4 plus pi over 4, which would be pi over 2, okay? Now, the angle doesn't actually change whether I'm talking about the large arc or the small arc. It'll be pi over 2 for both of them, okay? So I end up with this large arc. Remember that we said theta equals A over R. So if I want the arc length, it'll be theta times R, right? So this large guy here, the radius would be from there to there. So I've got the 5 and the 3. So that would be 8 times pi over 2. And then for the small guy, it's still going to be theta times R. Theta is still the same, pi over 2, but now my radius is different. My radius is only that 5 right there. Okay, so that would be 5 times pi over 2. So I end up with 8 times pi over 2 plus 5 times pi over 2 plus 3 plus 3. Okay, which is where that next kind of line of work was coming from. So 8 times pi over 2 right there, that's my big guy. 5 times pi over 2 right there, and then the 3 and 3. So stick all that in your calculator and get an answer for me. And you should have gotten 26.4 centimeters. So the perimeter of the lollipop is 26.4 centimeters, okay? All right, so always make sure you are reading the question very, very carefully. All right, good. Next up, we're going to review a little bit about angles and standard position. Let's just summarize what we've done so far. So a radian is more useful than a degree. Radian measure is related to two things, the radius and the arc length. To convert from degrees to radians, we use the ratio pi over 180. And then to convert from radians to degrees, we go 180 over pi. And then when finding the arc length, our sector angle must be in radians. That's super, super important, okay? All right, so now we're gonna head into just a quick review of angles in standard position. A rotational angle is made up of two rays with a common endpoint called a vertex. The two rays are called the initial arm and the terminal arm. So I would start at the initial arm and then I would rotate to the terminal arm there, okay? And then where the initial arm and the terminal arm connect, that's called the vertex. And then my angle would be in here. And you do need to show an arrow of where the initial arm goes to the terminal arm, okay? Because the arrow also shows you the direction of how you're rotating. You can imagine, I could have drawn you the same picture, but said, no, 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 this is theta. I'm gonna rotate from there to there, okay? And so we'll talk about that, but those arrows are actually really, really important in your work because it shows the direction you're heading. Okay, this is not an angle in standard position yet. This is just called a rotation angle. The way we make this an angle in standard position is we turn it so that the initial arm is sitting on the positive x-axis, okay? And then the terminal arm is somewhere in a quadrant and the vertex is at the origin, okay? So we're putting this on a coordinate plane. So the vertex is at 0, 0, and the initial arm is on the positive x-axis. So an angle in standard position, the initial arm is on the positive x-axis with the vertex at the origin. Positive angles are rotated counterclockwise and negative angles are rotated clockwise, okay? So you'll notice the arrow of rotation that I'm giving you there for theta. So that is a positive angle right now because I'm going counterclockwise. Just as a quick reminder, because sometimes we forget, quadrant 1 is here, quadrant 2, quadrant 3, and quadrant 4, okay? Okay, angles in standard position could be larger than 360 degrees, depending on the size of the angle, the terminal arm could be in quadrants 1, 2, 3, or 4. Sometimes the terminal arm could be on the X or Y axis as well. Those are special. They're called quadrantal angles. I'll write that down for you in a minute. What's important right now, though, to talk about is the reference angle. We use the reference angle a lot when we're doing this stuff. The reference angle of an angle is the acute angle formed. Wow, that's angle a lot. The reference angle of an angle is the acute angle formed by the terminal arm with the x-axis. Essentially, it's wherever you are on the terminal arm, it's the quickest way back to the x-axis, okay? And that's why we say acute. Acute means less than 90 degrees. It's the quickest way back to the x-axis. So in every quadrant, you have to look at it slightly different because you're like, okay, because sometimes you're kind of going down to get to the x-axis, but if you're in quadrant 3 or 4, you're actually going up to get to the x-axis. And the whole down-up thing doesn't matter because we don't call these positive or negative. We only ever call them positive, okay? Reference angles are always positive. Okay, so for each angle, sketch the angle and state its reference angle. So 100, now you should be pausing me for each one of these and trying them if you haven't been pausing me already. 175 degrees. You should be almost at the 180, right? I'm not looking for exact, I'm looking for a sketch. So I need to know you're in the right vicinity. So roughly there. Now what would the reference angle be? The reference angle is the quickest way back, so it's right here, okay? And that would be 5 degrees. Most of you can just do that in your head. But if you're unsure, or if you're talking about radians, like we will be in a minute, it would be 180 minus 175 here. Or in radians, it would be pi, because remember 180 was pi, pi minus whatever your theta was, okay? So the reference angle for quadrant 1, we ended up with 180 minus 175, and that gave us 5. Okay, so now you're going to try 40 degrees. So 40 degrees actually ends up in the first quadrant. And the reference angle is the same thing because it's the quickest way back. So in the first quadrant, the reference angle and the angle actually equal each other. Okay. Okay, 600. So you have rotated more than a circle there. So you need to think, okay, I'm going to go 360 degrees. And then how much more will I go? Well, 600 minus 360 will give you 240. So essentially I have to draw a 240 degree angle here, but I have to show that it's 600 degrees. And where I show that it's 600 degrees is that rotational arrow, okay? It has to go around the circle all the way and then around again to the terminal arm. Okay, if you just had an arrow that went from there to there, then you're not showing me 600, you're showing me 240, okay? Now, the reference angle for this guy, I would end up going the 240 that I know this is, okay, minus 180, and that would give me this leftover piece here. So the first thing I did, so just to be clear, I minus the 360 first, so I got down to a principal angle. I don't know if you remember that being called a principal angle or not. I'll have that written down for you in a second. But the principal angle, when we're dealing with greater rotations, the principal angle is the smallest rotation that would allow the same picture, okay? So I took away the 360 and then I took away the 180 to get the leftover piece. So the reference angle there is 60 degrees, okay? Okay, now pi over 2. Now I did 2 things to you here. Number 1, I switched you to radians. Number 2, well, I can't talk about number 2 until we know where this goes. So let's figure out where this goes first. You know that this is 0. Oops, that's a highlighter. That was stupid, sorry. You know that this is 0, and you know that this is pi, because we've established that pi and 180 degrees are the same thing. So, well, you guys are smart. Pi over 2 is halfway between 0 and pi, so pi over 2 has to be right here. So you know, even without converting, and I don't want you, my goal with this is not to have you sit there and convert everything to degrees, okay? That is not the purpose of this. I know lots of teachers teach that as a strategy, and it is a strategy to get by, But my goal here is to have you be able to think deeply about trigonometry. And you will not be thinking deeply about trigonometry until you force yourself to think in radians, okay? I really want you not to shy away from the radians, but to embrace the radians and really think through the radian measure, okay? So now we know for sure, though, without even doing a conversion, that pi over 2 and 90 must be the same, right? Because it's in the same spot. Now, the other thing that's special about this is I am actually on an x-axis. Sorry, the y-axis. I'm actually on an axis. I go from the x-axis to the y-axis. That is pi over 2. Now, where that becomes a conversation is when I ask you for the reference angle. If you will recall several slides ago, I said that the reference angle is the acute angle between the terminal arm and the x-axis. Acute means less than 90 degrees. The 90 degrees is not less than 90 degrees. So these are special angles. They're called quadrantal angles, and they don't have a reference angle, okay? Can you think of any more? Well, pi is one. We're looking at that. 0 could be 1, 2 pi. What's halfway between, like this would also be 2 pi, right? Because that's a full circle. What's halfway between pi and 2 pi? 1.5 pi, or 3 pi over 2, right? So 3 pi over 2 would be down here. So that's also a quadrantal angle, okay? Awesome. Okay, then we have negative 2 pi over 3. Now, the negative refers to a direction. And again, I don't want you to convert this. I want you just to think through. If from here to here was pi, then don't you agree that from here to here would be negative pi? Okay, I'm just going in the other direction. So negative 2/3 would be 2/3 of that orange rotation that I just did. So where does 2/3 of that orange rotation show up? Well, it shows up right about there, right? This would be like 1/3, 2/3, 3/3. So negative 2/3 pi would look something like that. Now, the reference angle, remember this, essentially for the reference angle, I'm going to go back and think about this as positive. Whether you call that pi or negative pi, it doesn't really matter right now. Just think about this. If that's 2/3 of the way to pi, how much is left over in here? Well, I have 1/3 pi left over. So the reference angle here is going to be pi over 3. Okay. So I just went pi times, or pi minus the 2/3 pi to get the 1/3 pi. Okay. Okay, now I mentioned the principal angle a couple minutes ago. These are definitions I expect you are vaguely familiar with because you did them in 20-1, but just in case. Coterminal angles are angles drawn in standard position that have the same terminal arm, okay? So the example there would have been 240 degrees and 600 degrees, okay? Principal angle is the smallest positive coterminal angle. So between the 240 and the 600, 240 would have been the principal angle, okay? Name a positive and negative angle that are coterminal with 300. Well, if I want to get a positive and negative angle coterminal with 300, all I need to do is add 360 to 300 or subtract 360 from 300. So if I add 360, that would be 660. If I subtract 360, that would be negative 60. Okay, so 300, 660, and negative 60 are all coterminal to each other. Now, you can imagine, I don't have to just add 360. I could add 360 times 7. I could add 360 times 18, right? There's an infinite amount of coterminal angles that we can do. So that moves us into another conversation called the general form. So general form essentially describes all of the angles. So what I do is I essentially say, okay, I start with my principal angle, my first positive, which in this case is 300. And then I can say I will add 360 degrees, any multiple of 360 degrees after that. Okay, so we say 360 degrees n. And then we say, now, there's a couple different ways we can say this. In this one, I defined n as a member of the natural family. So counting numbers, 1, 2, 3, 4, 5. And I said I could either add or subtract that. See that plus minus there, okay? The other way to do that is we could just say theta plus 360n and then say that n is a member of the integers, because then integers allow for the negative direction, and that'd be fine too. Then we can also state this in radians. So in radians, we would go plus 2 pi n, and then either have the plus or minus in front and say it's a member of the naturals, or have the just the plus and say it's a member of the integers. Okay, so theta here represents my my initial principal angle. On a diploma, the most common thing I see, and like you gotta, part of 30-1 is you start realizing there are multiple ways of representing math, okay? And so you have to be okay when things aren't done the way you do it, okay? As long as it's still mathematically correct. Many of you might use Z for the integer family, totally fine. I will use I when I'm talking about integers, mainly because this one is the predominant thing that I see on the diploma, okay? They say theta plus, and then they say n is a member of the i's. And then 2 pi n, just for clarification, because I don't want any confusion, 2 pi n, I've seen written on a diploma as 2 pi n, I've seen written on a diploma as 2n pi. It really comes down to the preference of the teacher who wrote the diploma question. There's no standard for that. So don't worry about that. It can be written either way, okay? I personally like 2 pi n better just because I feel like 2 pi is the number and then you're multiplying it by n. So that's why I would do it that way. So when we put this all together in this particular question and we write 300 degrees in general form, we would end up with 300 plus or minus 360n, where n is a member of the natural family, or 300 plus 360 degrees n, where n is a member of the integers. And you can use I for integers, you can use Z for integers, doesn't matter. Just be comfortable seeing things that might be different than how you know to write them and understanding that there's still the same thing, okay? All right, so now to end this note, what you want to do is we're going to just quickly draw some pictures of what the sine of theta graph would look like and what the cos of theta graph would look like. We're also going to practice some conversions. So I've given you, it's a larger table than this. I'm only going up to 180. And then we'll switch slides and I'll give you the rest of it. But the first thing I want you to do is pause me and take all those angles and convert them to radians, okay? So that's the first thing. Give me a pause and do that. Just go to 180 and then we can follow together. Okay, and so this is the one you should have gotten for that. So 0 is 0, 30 is pi over 6, pi over 3 for 60, 90 is pi over 2, 120 is 2 pi over 3, 150 is 5 pi over 6, and 180 is pi. Now what I want you to do, and this is where it matters what mode you're in your calculator. I want you to tell me the sine of theta. Now, if you are looking at theta as degrees, you need to be in degree mode. If you are looking at theta as radians, you need to be in radian mode. Okay, so a reminder to get to switch modes. If you're a Casio kid, you will go shift setup and then go down to angle. And you have your F1 and F2 and F3 will toggle between degree, radian, and radian. So just pick the one you want and then just exit. If you are a TI kid, you'll press the mode button and go down 3, right 1, hit enter on degrees or leave it in radians, just whichever one is highlighted there, that's the one you're in. Okay, so the mode matters, but in 30-1, you will be constantly switching between modes, just depending on the question you're doing, depending on what you need. So it's not like we've trained you in 10, 11, oh, you always have to be in degree. Not so in grade 12, you'll be switching back and forth all the time. Okay, so now I want you to figure out the sine of essentially 0, 30, 60, 90, 120, 150, 180, and the cos of 0, 30, 60, 90. And just round to a decimal place for now, where we won't look at exact values. Okay, so pause me and you try that. Okay, and so that would have given you these guys. Okay, and I'm going to show you this as a graph in a minute. We'll put it all together, but just make sure you've got the same thing there. And again, I'm rounding to just one decimal place for now. Okay, so now let's look at the back half of your angles. So let's first pause me and convert all those to radians. Okay, so you should have 7 pi over 6 for 210, 4 pi over 3 for 240, 3 pi over 2 for 270, 5 pi over 3 for 300, 11 pi over 6 for 330, and 2 pi for 360. Now, find the sine of all the angles. You can choose degree or radian, doesn't matter. And find the cos of those angles. Okay, and these should be your answers. And now what we're going to do is we're going to put all that together into a graph. Okay, so let's start with the sine graph. So this is y equals sine of theta. So I'm going to do this in degrees. And essentially, we're just going to take the table and plot those points. So we knew that the sine of 0 was 0. We knew that the sine of 30 was 0.5. We knew that the sine of 60 was about 0.9. We knew that the sine of 90 was 1. We knew the sine of 120 was about 0.9. We knew the sine of 50 was 0.5. We knew the sine of 80 was 0. We knew the sine of 210 was negative 0.5. The sine of 240 was negative 0.9. The sine of 270 was negative 1. Sine of 300 was negative 0.9. And the sine of 330 was negative 0.5, and the sine of 360 was 0. Now, you can see, just the way I did my dots, you can see this wave, okay? So your job would then be to draw this in, and I'm gonna do a crappy job of this right now because I'm holding a mouse doing this live, but I'll do the best I can. Don't laugh at me, please. The goal would be one smooth line like that. It wasn't bad, but I have marked these on diplomas, so I'm going to tell you, here's what is bad. Here's what we wouldn't want to see. I have a bulge right there. Do you notice that? I kind of come out. I shouldn't have that overarching bulge, but the rest of it actually wasn't too bad. Okay, now to show you, this is like the cooking show. I already have it ready to go. A computer generated drawing of that would look like this. Okay, so that's the sine graph. Now what I'd like you to do is pause me and try the cos graph. So do the same thing, plot each one. 0 is 1, 30 is 0.9, and just go through the whole thing just like I did with you. And then for the cos graph, you should get something that looks like this. Okay, and now I'm gonna leave you with a little bit of an aha moment. I'm gonna superimpose both of these on the same graph together. And I'm going to say, hey, look at this. The blue is the sine graph. The red is the cosine graph. I want you to notice there's actually no difference between the sine graph and the cosine graph, with the exception of a translation. One's been shifted left or right of the other. Can you see that I could take that blue and shift it to the left, and I could make it be on the red? Okay. And we'll talk more about that as we go into things. This is just kind of an introduction to what they look like. Okay. Collectively, sine and cosine graphs are called sinusoidal waves because they create this repeating periodic pattern over and over and over again. Okay, so we're going to leave it there for now. Your homework has been posted for you, and you're going to go through this. Don't forget to do that prereq stuff as well. And if you have any questions, please feel free to connect with me. Okay, have an awesome day, guys. Take care.